Jai Hind everyone. I am Nikita Jaiswal from Civil Engineering Department, Ajay Kumar Garg Engineering College, Ghaziabad. So today we're going to discuss the further turbulent flow. We have started turbulent flow. We have seen the various concept. Now we are going further in this video. We have gone through, again we are repeating it, the shear stress in turbulent flow. The shear stress in turbulent flow is a combination of viscous shear stress and turbulent shear stress, as we know very well. Viscous shear stress is what? It is a stress contributed to fluid flow due to the viscosity in between the layers. Now how we can formulate it? By using a formula tau equal to mu du by dy, where du by dy is your velocity distribution and mu is your viscosity. Okay, and now what is your turbulent shear stress? So there are many equations given by many scientists, many researchers who have already given some equations. Let us suppose the first equation we are going to study today is J. Bossenis, who was French mathematician, who has given an equation for turbulent shear stress as eta dv by dy, where your dv bar, or you can say dv, is actually your time average velocity. Time average velocity again from what? At a distance y from boundary. Okay, so here v bar is your time average velocity at a distance y from the boundary. Now what is eta again? Eta is your turbulent mixing coefficient or eddy viscosity. You simply can write it as eddy viscosity. Okay, divided by rho, we'll get it as epsilon, or you can write it as simply you can write T. Now T is actually your kinematic eddy viscosity. Okay, now eta is again, eta actually depends upon the characteristics of flow. Okay, so how much the particular flow is turbulent, so your eta will be more if the flow is very much turbulent, or turbulence, the amount of turbulence is very high. Okay, so the value of eta, it depends upon the Reynolds number of turbulent flow also. If the Reynolds number for particular kind of flow is more, the value of eta will be more. That's why we say that the function, that eta is function of characteristics of the flow. Okay, now we are going to analyze what is Prandtl mixing length theory. Okay, Prandtl mixing length theory was actually that particular theory was given by Prandtl again, where he has formulated the velocity fluctuations. Okay, how the velocity fluctuations in x direction and in y direction relates to velocity gradient. Okay, so he has given a formula where you can say velocity fluctuation v dash is equal to L dv bar by dy. Here he have given L as, we have formulated L as mixing length, as their mixing length. Okay, now again shear stress in turbulent flow, we already have talked about this slide. L is your mixing length, or you can say Prandtl mixing length. What is L? How you can formulate L? L is equal to average distance perpendicular to the direction of flow, a small fluid mass which travel before its momentum is changed by the new environment. Okay, now expression for turbulent shear stress is what? Will be what? Tau equal to rho L square dv bar by dy square. Okay, so this is the equation formulated and given by Prandtl. We can use it as turbulent shear stress. Okay, just apply addition of both the viscous and turbulent shear stress, that will be your total shear stress in any kind of turbulent flow. Okay, so you can write it as this equation like this. Okay, now again, when we are going to calculate the head loss, okay, the head loss in any kind of turbulent flow, so how you are going to calculate? The equation, Darcy's-Weisbach equation, we know very well. We can use that particular formula in here also. Okay, your HL will be equal to FL V square by 2GD, right? Now, what is your hydrodynamically smooth and rough pipe? How we can define it? It depends upon the length of laminar sublayer and the length, or you can say not length, actually the height of laminar sublayer. Okay, height of laminar sublayer, we know very well what is laminar sublayer. This is a zone in turbulent flow. That particular zone, in that particular zone, the flow characteristics is actually laminar. Okay, or you can say the flow behaves like an laminar flow. And now here you can see that distance from here to here is actually the distance or height of laminar sublayer. Here you can see the distance k, or this distance k is you can say this is your equivalent uniform sand grain roughness, or you can say the average height of roughness. Okay, for an example, this is your k. Let us suppose if your laminar sublayer height is more than the roughness height. Okay, what we will say? That pipe is, in this particular case, what we'll say, the pipe is smooth, or you can say the boundary is smooth. Okay, but on the another case, just opposite of that, if the laminar sublayer is actually less than the equivalent sand grain roughness, so what you will say, what you are going to say, that the particular pipe is rough. Okay, or by experimental investigation, you can say there are another experimental investigations who can differentiate between smooth and rough boundary. Here you can see another expression which states k by del is less than 2.5, then you will say that is a smooth boundary. If it is greater than 6, you will say this is rough boundary. If it is in between 0.25 to 6, you will say boundary is in transition. Okay, now the velocity distribution in turbulent flow in pipe. Now you can formulate it by using Prandtl equation. What Prandtl again says, that the length is actually proportional to y. What is y again? It is the distance from boundary. Okay, when we move away from the boundary, the length or the Prandtl length is proportional to y. Okay, you can say it. More far from the boundary, more the value of L will be. Okay, now say here L is proportional to y. Okay, or you can say the Prandtl length is proportional to distance from the pipe wall. When you remove that proportionality sign, you will get as kappa, or Karman universal constant. Okay, the value for Karman universal constant we assume as 0.4. How you can assume it again? Actually, there is another equation given by Prandtl as L equal to 0.4 y minus 0.44 y square by r. This term is actually very negligible when we talk to the very close to the pipe boundary. This term is very very negligible. So by comparing this equation and this equation, you can get kappa as 0.4. Okay, kappa is again what? Karman universal constant. Okay, now for y is to be very small, if your y is very small, what you are going to get it as? Kappa is 0.4. Okay, again the equation for tau is what? Rho L square dv by dy whole square. Okay, just put kappa y in place of L. What you are going to get it as? Tau, then the new equation for tau is now rho k square y square dv bar by dy whole square. Okay, now the shear stress also varies linearly with the radius. Okay. If let us suppose you are considering this pipe, okay, you are considering this center line Okay, you can show here that the radius of pipe is capital R. Let us suppose from any distance y from the pipe wall, the shear stress is tau, and obviously at the pipe wall, the shear stress is tau naught. Okay. Now from here to here, the distance is r, small r. Okay. So because shear stress varies linearly, you can write the formula like this. Okay, just apply linear equation on in triangular formula. What you are going to get it as tau by tau naught equal to small r by capital R. Get a equation for tau as tau naught r by capital R. Okay. Now just put a small r as capital R minus y. What you are going to get it as tau equal to tau naught 1 minus y by capital R. Okay. Now for very close to pipe wall, what you are going to say, tau equal to tau naught again. Write the equation, the previous equation in form of wall stress. Okay, we will get it as tau naught as equal to rho k square or kappa square. Okay, k is here what? Kappa. The value for kappa is 0.4. Rho k square y square, again velocity gradient square. Now find an equation for dv by dy. Okay, you will get it as 1 by kappa y root over tau naught by rho. Okay, here this particular term tau naught by rho root over tau naught by rho is actually having a unit equal to the velocity. Okay, so we can call it as shear velocity or friction velocity. You can represent it as v asterisk. Okay, put the v asterisk in this particular equation. Now again you will going to get it as the equation like this. Okay, our purpose was to find out velocity equation for velocity. Okay, just you need to just integrate that particular equation. Okay, integrate once. What you are going to get it as, because v asterisk and kappa is your constant. Okay, the only variable here is y. So integrate 1 by y, you will get it as log y. Okay, plus c, a constant of integration. So here you can see that the velocity distribution is actually logarithmic in nature. Okay. Now apply the boundary condition at the center of pipe. What you will going to get it as y equal to capital R, v equal to v max. Okay, again I am see at y equal to capital R, the velocity at center of pipe is maximum. Okay, so you can write it as v equal to v max. Okay, now just put in the above equation. Okay, put in the above equation and you will going to find out the equation for constant. Okay, integration constant. Now put that particular constant in this previous equation, solve it, you will going to find out. Okay, solve it, that means put a value of kappa as 0.4, you will finally going to get the formula, final velocity distribution in turbulent flow in terms of Prandtl equation, or you can Prandtl concept, you can say. The final formula for velocity will be equal to 2.5 v asterisk log y by r plus v max. Now the equation is known as Prandtl universal velocity distribution equation. Why universal? Okay, you can apply in the both the situation, rather the pipe is smooth or rather the pipe is rough. Okay, you can apply this formula. So that's why it is your universal velocity distribution equation. Okay. Now velocity distribution for turbulent flow for hydrodynamically rough and smooth pipe. Now we are categorize equation for rough and smooth pipe. Okay, so now the velocity distribution for turbulent flow. Okay, this is equation, this is your previous equation. Okay, previous equation is what? V equal to previous equation, that means the basic equation. Okay, here we have just formulated the basic equation like this, v equal to v asterisk by kappa log y plus c. Okay, so here what the actual condition states, when you apply the derived equation to the actual form, or you apply some experimentations, okay, what you are going to get, as we do not what theoretically what we say, that the velocity at pi wall will be 0, okay, or you can say at y equal to 0 velocity will be equal to 0, the theoretical concept. But in actual situation, what actually happens or you apply in the same formula, what you are going to get as you will not get velocity at 0 at y equal to 0, okay, or you will get it as minus infinity. So what we assume that according that particular derived formula, we will assume, okay, that at y equal to 0, v equal to not 0, okay, we are considering it, but at some distance from the wall, let us suppose some distance, let us suppose y equal to y dash, okay, the velocity will be equal to 0, okay, let us suppose. Now the actual condition we have stated in this slide like this, okay, at some distance, let us suppose at some distance y equal to y dash, p will be 0, okay. Now in this formula, put y equal to 0 and y equal to y dash, okay. Now again formulate the equation for constant. Here you can see the equation for constant is minus v star by or v asterisk by kappa log e y dash, okay. Now put the value for c again in this equation, what you are going to get it as equation like v equal to v asterisk by kappa log e y minus v asterisk by kappa log e y bar y dash, okay. Now just forget that equation we have just formulated, okay. Now come to how we can use that formula in again in the new concept or new topic in velocity distribution in smooth pipe, okay. We know how we can write equation for shear stress in a linear form, okay. Now here in a smooth zone or in a smooth pipe, we can say that there will be a linear distribution in zone close to pipe boundary. So we can write this as dv by dr as equal to simply v by y, okay. So now the viscous shear stress predominate the turbulent shear stress in case of smooth pipe, okay. So when we'll write the the final equation for shear stress, what we are just doing that we are putting velocity gradient as equal to v by y in viscous stress formula only, okay. Now just divide by rho in LHS as well as RHS, okay. So this equation will become as, see, we are writing equation for shear stress in boundary, okay. Now what you are going to get it as tau naught by rho, that is the whole that is actually equal to v asterisk square, okay. Now the equation will become like, you can transfer v star to here, okay. Just take an equation for p by v asterisk or v star, okay. You will going to get the equation like this, v star or v asterisk y by mu, okay, where here mu is your kinematic viscosity, okay. Now this actually applicable, this equation, okay, this equation is actually we are writing that is applicable for y equal to 0 to y equal to s dash or del dash, you can say, or you can say this is the zone for laminar sublayer, okay. Okay, we have started from the zone of laminar sublayer zone, okay, where we have assumed that there is a linear distribution of velocity. So we have taken dv by dy as v by y, simple. Now Now, okay. Now, various experiments already have worked upon this particular equation, okay, which have stated that, see, there are two equations written here. You need to remember it, okay, that V star S dash or del dash by mu is actually equal to 11.6, okay. This is, you can say, at the boundary of laminar sublayer, okay. You can get the formula or the value for this particular equation as 11.6, okay. And when that particular equation, you can write the same equation, but the height is again y dash. Y dash is what? Where your velocity, so the actual velocity is 0, okay. So this equation, you can get the value for this equation as 0.108. So formulate the value of laminar sub layer height or thickness of laminar sublayer. You can get it as del dash is equal to 11.6 mu by V star, okay. And your y dash will be equal to 0.108 mu by V star, okay. And now the equation we have formulated just before 2 slides. You can play back, okay. You can get, you have already formulated this particular formula, okay. And now in this particular formula, just put this equation, okay, which contains 0.108 mu by V asterisk, okay. Put in this equation, put all the other values, okay. As kappa we know it is equal to 0.4, okay. Put kappa is 0.4, change it to log 10, okay. Change it to log 10. What you are going to get it as? The same equation now you can write it as 5.75 V asterisk log 10 V asterisk y by 0.108 mu, okay. Again you know, again simplify it. What you are going to get it as? Just take the parameters or variables in one equation and other numeric variables in another equation, okay. So write it, solve it, you will get in this particular equation the value for this equation is 5.5, okay. So now the equation for, or you can write a velocity equation for smooth pipe, you are going to get it as V by V asterisk equal to 5.75 log 10 V asterisk y by mu plus 5.5. Now this is your velocity distribution equation in smooth pipe, okay. This is done. Now the same way you are going to calculate again the velocity distribution equation for rough pipe, okay. Now the rough pipe, so there are again some experiments which have concluded and said that your y dash, where your actual velocity is 0, is equal to kappa divided by 30, okay. Not kappa, sorry, this is actually, this is k. Here your k is average height of pipe roughness, okay. This is not kappa, this is k, okay. This is average height of pipe roughness. Now height of pipe roughness divided by 30 is, it will be equal to your y bar, okay. Now again we are writing the previous equation where we have substituted y dash as k by 30, okay. Convert log e to log 10, convert log e to log 10. What you are going to get it as? V by V asterisk equal to 5.75 log 10 30 y by k, okay. Now here you can get it as V by V asterisk 5.75 log 10 y by k 5.75 log 10 30, okay. Just convert this particular equation to numerical value. What you are going to get it as, okay, as 8.5. So you can write the final equation for velocity distribution in here we have started for rough pipe. You can get it as V by V star 5.75 log 10 Y by K, okay, K plus 8.5. So now we have just arrived how you can differentiate between rough pipe and smooth pipe. Why? In terms of velocity distribution equation, okay. So again we have started from the shear stress in turbulent flow, okay. There are two equations, Bosnick equation and another was your Prandtl mixing length equation, okay. We do not going to do any numerical based on this equation. We'll do some numericals based on your mixing length concept, okay. This is how the hydrodynamically smooth and rough pipe and the velocity distributions can be formulated. See, when we talk about laminar flow and when we talk about turbulent flow, okay, so there are various variations in both the flows. See the analysis or derivations associated with laminar flows are actually somewhat very much easy, okay, not like turbulent flow. In turbulent flow, there are various equations, small equations you need to find out, you need to remember, actually you need to remember, because this is actually experimental based and you do not have any particular derivation for it. See, you are deriving after you are getting some inputs from somewhere. For an example, okay, I am mentioning this again because this chapter is little bit complex, will feel it little bit complex, so you need to derive it again and again, you need to remember it. For an example, when you are deriving this particular equation, you have to remember that the velocity gradient you will put at as equal to V by Y here in this equation. And also when we were talking about this particular equation, we have directly applied as V asterisk S dash by mu as equal to 11.6 directly here, right? And also V star Y dash by mu as equal to 0.108 directly here, because here this equations is actually experimental based, okay. If we go further, if we study deep, okay, we can get it how we are going to get it, but actually it is experimental based, so you need to remember it for your exam purpose, okay. So there are very small formulas in this particular chapter, okay. So this is for all for today's lecture. Thank you.